Okay, so my name's Phil White. I'm the Chief Architect at Scale Computing. And I'm going to talk a little bit about the technologies we have in our product that make these things possible, to make things simple and easy for everyone to use. So obviously our goal is complete simplicity. We target, I guess, a unique market in that case, in that we're going for the most simple solution as possible. And we're using Linux clusters, probably one of the most complicated things you can imagine, at least certainly that I can imagine. And it was actually quite surprising. I've been here for about 5 years, and some of our first, I guess, few major versions of our product, version 1 and version 2, we noticed an interesting trend in that our support load would increase linearly with the number of customers. Obviously, that's not scalable, right? And so we knew we had to change something, and we did. Starting in the third of our product, we essentially did a complete rewrite of our entire management layer. And we introduced some new, pretty novel technologies, and that's what we're going to talk about here. So the bottom line is we need a solution with cluster management that hides the complexity of the Linux cluster and handles failures automatically and automates everything. I mean, that's the bottom line. And you can imagine there are, with clusters and partitioning, there are some fairly complex failure scenarios that can occur. And we would rather handle that sort of thing automatically rather than having somebody call support. And since the release of our third version, I wish I had somebody from support here to back me up, but our support load has gone down dramatically and is incredibly low these days, as well as our net promoter score, kind of speaking the same thing. So again, our assumptions these days are that everything will ultimately fail. Hardware obviously fails, but software fails as well. On a Linux machine, there's quite a few open source components we use, and they don't always behave as expected. And sometimes they operate out of their design goals and their design constraints. So we have to have a software management layer that can almost anticipate those failures and make the correct decisions even in those situations. So we design for those failure modes, known and unknown. So you've seen the UI. And it's a nice point-and-click UI, and it's covering up quite a bit of technology under the hood. And so let's talk about that. The first thing I want to talk about is what we call our data layer. And there's a few other components that sit on top of this data layer. It's definitely tied in with the UI, and we'll talk about those other components in a moment. But first, concentrating on the data layer itself. There's 3 layers there: collectors, checked values, and conditions. First of all, collectors. These are essentially like sensors in a car. You're basically collecting some piece of data. It might be the amount of free disk space in the system partition, the temperature of the chassis, the error rate on an Ethernet interface, these sorts of things. All this data is being collected. And they're all very simple, so that the code itself does not try to make any decisions based on that data. All it's doing is collecting. So they're very simple and very modular. So we can, that code can be reused. The code can be unit tested and very easily. So one layer above that, we have where we call checked values. And this is where that data from the collectors ends up. Now these are very carefully controlled variables in that they have to be initialized, valid, and fresh. So these values can't actually be read unless those preconditions are true. First of all, some collector has to have run and populated data there. The data has to be valid, meaning it's within a range that we're expecting. If we're collecting an error rate on an Ethernet interface, it shouldn't be a negative number coming back from the driver. You can have a firmware bug. We've actually seen that in a firmware bug where the numbers just get out of whack. And if you were to pay attention to those numbers, you might make a bad decision. So the checked value kind of guards against those type of problems. And freshness is important as well. If for some reason a collector makes a system call and that call blocks for some long amount of time and suddenly this data is no longer fresh and it's old data, you don't necessarily want to make decisions based on that. So that sort of metadata is stored along with the value itself. So on one of our clusters, we'll have, there's thousands of these checked values. It's data we're collecting from all aspects of the system. And it gives us a consistent view of the system that all of our tools, all of the UI, all the state machines, which we'll talk about in a moment, and the alerts, all that stuff is using the same database of information. So the example I like to give of a checked value, and this was actually kind of the inspiration for it, is the heading indicator in an aircraft. You know, the heading indicator is actually still showing you that you're heading almost south here. But the problem is you've got this heading flag is indicating that your gyro is bad. So would you want to actually use that information? No, you're gonna be in for a surprise. That's what the check value is it's showing you that you've got a problem with the number that you've collected. So again, uninitialized data, invalid data, if it's expired or if the poll or the collector has thrown some sort of exception. You need to know that information. These check values are also cluster-wide. So every node can view all of the information about all the nodes in the cluster. And we have command line access to this information. And again, as I mentioned, the UI will display some of this information for some of those gas gauges that you saw in the UI. So again, I've mentioned some of these already. You know, and a lot of the information about every VM guest that runs when a VM starts up, several check values will get dynamically created, and the tracking information about that VM, its memory usage, etc. So the top layer here is, these are called conditions. And these are very simple. It's just a Boolean value. You can think of it as like a flag, like there's some sort of problem. And we've built in some intelligence in there. So, you know, essentially it's going to indicate an undesirable state. If that Ethernet error rate that we're collecting into a check value goes over some threshold where we decide, okay, this is actually a problem, that's when you would set a condition, right? So the conditions will be watching those check values, and then when something gets out of range that we've predetermined, the condition becomes set, and that's I guess the point at which we know we need to do something. We can send alerts. We can actually take action on that. The conditions have some nice features built in as well that really give us some good functionality. In particular, queryable history. This might not seem that cool, but it's with troubleshooting, it's unbelievable, because you can actually, if a customer calls support and they say they had some problem this morning, and you get on the cluster and now it's fine, something's corrected itself, you can go in and just run one command on the command line and see, okay, here's a list of all the conditions that were set. Oh, look, this Ethernet interface went down at 8 a.m. this morning. That history is stored in every condition. So from a troubleshooting standpoint, it lets us find problems with a particular cluster almost immediately. Whereas prior to this release, I mean, every support call was an exercise in Linux problem determination, which can go on for a long time when you're really trying to nail down what's going wrong. Additionally, we can configure set and clear delays. So if we have a condition that tracks low memory, a case of low memory, and memory usages can be somewhat volatile, we want to make sure that memory usage is actually going to be low, or the memory usage will be too high above a threshold for some amount of time before we would actually say, yeah, we've got a real problem here. So these conditions tie in directly with pretty much everything in the system. The UI, the degraded light in the UI that goes on, all of those indications, and I'll pull up a UI here in a moment, but they're all tied directly into conditions, as well as alerts. Syslog and email alerts get triggered directly from the condition systems. And then the conditions, of course, log, which we don't expose condition logs to customers right now, but that is something we could do in the future. Obviously, our support team finds it very valuable as well. So again, you can just think of conditions as being a flag that goes up. System free disk space is below a threshold. We have a condition now that will set that. You'll get an alert, and you can handle it. And then these failures that we talked about, the collector fails, the check value becomes invalid. Those sorts of errors and exceptions actually propagate all the way up, so that say you have a collector that's gathering the amount of free memory on the remote node, and you're looking at a check value, and you have a VM that needs migration, you don't want to migrate it to a node where the free memory collector isn't actually functioning and it hasn't collected any data in 6 hours. We don't know that. So we're not going to make a decision based on those conditions right now.
So Phil, how much overhead is this to the environment?
It's actually very low. There's all of these polling rates can be adjusted. Some of the collectors are sort of like edge triggered, like there will be some event that'll happen, and so that helps. But to be honest, like not everything in Linux can be collected through that fashion. You have to poll many things, and that's actually an interesting technical detail about this system that I normally don't share, but it's pretty interesting. So we have the timestamps of the last collection of all this data. that gets pushed through all the way up to a condition, and you can view that on a condition. And the automated systems, the state machines, which I'll discuss in a moment, will actually look at that timestamp and decide, okay, it looks like we need to take some action, but the timestamp isn't yet, it's basically too old. We moved into the state we're currently in after the data was collected. And what we can do is we can sort of prod the collector. Okay, we might need to make this transition in the state machine. Please collect the data again, just so we're sure, right? And so that optimization has let us really reduce the poll interval on a lot of these things, because now we're actually only actively polling them rapidly when it's actually important to look at that data, as opposed to, normally, you might not need to collect the amount of free disk space in the system partition.
So you're saying you could almost do that dynamically, so you know that, for instance, on disk space,
yes,
you knew you had so much disk space, chances are it could never be used up that quickly. So
right, you're not going to max it, yeah.
There's no point polling every second to measure that, because you'll never use it up.
Right.
There's no periodic call home where all this data would be dumped on like a daily basis or something like that? It's only dumped when there's a call or something like that?
Yeah, when there's a support call and they open up that support tunnel, you saw in the interface, and then we can actually then SSH in, and this is usually like the first thing we look at, right?
Yeah,
you just run this command, and it's like, boom, here's all of these really obscure sort of problems. Actually, let me go to the next slide, and I'll kind of show you this. I don't know if this is readable, but some of the things like clock skew over a threshold. In a clustered system, your clocks have to be synchronized, but I can't tell you how many systems I've been on. You're trying to debug all these weird things that are happening, and you never even thought to look at the clocks. Right, because there's one of them that's in the wrong time zone or something like that, and suddenly here you are, you log in and you say, show me the conditions. And it's like, boom, clock skew over threshold. Well, that's easy to fix, and that's what's actually causing all these other problems. So that's really the value in the system, and you can quickly see, okay, well, here's a condition that's set. My alerts are unconfigured. That's not a big one, but I've got a backplane interface down on a particular node, and you can see the timestamps that it was last set and last clear. So that's very useful information that lets you really get to the root of a problem very quickly. And in many cases, as you'll see, the state machine that sits on top of this can actually automate that sort of correction of these conditions. So that's sort of the data layer. That's a quick overview of how that works. And then, as I mentioned there, we have state machines and an alert manager that sort of sit on top of this, as well as the UI. And the state machines are really the component of the system that's responsible for taking actions on any of these conditions. The state machines only look at the conditions. It's a sort of a pure separation of the logic of handling a condition versus the actual collection of the data. So by separating this out, it gives us some added side bonuses of that these things become extremely easy to test. We can create a mock data layer in software and just say, okay, I want to down this interface, and it's trivial for us to do that in automated testing. And that's one thing that we firmly believe in here is the automated testing of every one of our components. And with that, we do that with the state machines. As well as the alert manager. The alert manager is fairly simple, but you can imagine like a condition becomes set. A lot of these really might not want to know about, but in many cases, yeah, we want to get an email or we want to get a syslog when a condition becomes set or clear. And you can trigger those on either case. And that's all actually configured by a database, so that could be extremely configurable. We don't expose that again to the user, but we've made, support has made tweaks in the field where somebody wants an email when some particular condition gets set. We can add that very, very easily.
Any SNMP?
We don't currently support SNMP. I don't know that we've received a lot of demand for it, but I mean, again, that's a component that could be very easily tied into this as well. Triggering SNMP traps on a condition transition, right? So
you collect all this data, but have you ever thought to move all this data on the cloud and do analytics on all your customers instead of only one?
There's been, the support team has actually voluntarily asked several customers if they'd be willing to provide us with this data, and we just started doing that recently, only with a select few customers. And I don't know if anyone else has. I haven't been too closely involved with that project. If anyone else has any more details on it, but yeah, there's certainly a lot of interesting data that could be collected, in aggregate from everybody. But that possibility is certainly there. So again, the goal of the state machine is really just to make decisions and perform actions using these trusted set of inputs. And the interesting thing about the state machine is that there's really two things there. There's the state machine framework, which I'm going to talk about a little bit, but the structure itself of the state machine is really what's encoding this knowledge. It's sort of an automated sysadmin that's able to keep this knowledge, and this is kind of one of our closest guarded IP is really the structure of our state machine, how we can manage these Linux clusters and how we can correct complex issues in a Linux cluster by using this system. So one of the interesting things here is that this state machine framework is actually homegrown, and there's a few reasons for that. In particular, asynchronous actions are really important with a state machine that's running on top of a storage product. You can think of a state transition might be transitioning from a degraded system to a clean system, and that transition is a disk recovery that could take 6 hours or something like that, right? So that transition that's running it needs to be done asynchronously and in a way that it's not going to block the execution of the state machine that might be handling other orthogonal tasks like managing virtual machines and bringing up disks on other nodes, that sort of thing. So that's one of the very important features of our state machine framework. Additionally, it has to be dynamic. The structure of the state machine changes as you change the configuration of your system. When you add a new virtual machine, we actually create a new region in our state machine that manages that virtual machine. So you can imagine the state machine growing and changing as you're adding in virtual machines, as you're adding nodes, this sort of thing. History logging is pretty cool. Again, this is sort of like the condition log. The history log of the state machine is fantastic for support. Something may have gone wrong. We can get in and say, okay, show me the history of the state machine. We can get it's pretty cool. It shows a textual display. You can step forward and backward in the state machine and see what exact states the system has gone through. Exception integration. This is useful for us because we do a lot of, most of our development is in C++. We use heavy use of typed exceptions and things like that. And a state machine framework should be able to transition differently based on different types of exceptions that get thrown from, say, a predicate evaluation in a transition. So that's something that we added, and full type awareness of exceptions is very, very useful. As well as perfect integration with the data layer. Now that's probably the best reason for building this ourselves, is that we can define state machines that tie directly to conditions being set. We can take transitions on check values being out of range. All this stuff integrates perfectly. So again, I'm going to actually move on and show you a little bit of just a brief demonstration of how some of this stuff works. Let's see here.
Phil, when you started talking about data layer, I thought about the storage, but you're talking about the sensing and all that other stuff.
Yeah.
So you're going to get the storage later, I guess,
yes,
right?
absolutely.
Right. I'll shut up.
Storage field day.
So what I've done here is I've just set up a terminal window, and what we're looking at here is a state machine display. This is actually somewhat of a small sub-region of the overall state machine, but I'm displaying the region that represents the first slot in one of the nodes, right? And so at the high level, you can see, okay, we're in a state called drive present. Well, underneath the state drive present, we're doing several things, right? We're doing some drive handling. We've identified that the electronics of the drive are functioning. That's important to know because if someone inserts a drive, we've seen failure modes of drives where you can insert it, the kernel recognizes it, but you can't actually get the serial number off of it. It's in some weird state. The thing's just screwed up, but it still kind of works. You don't want to use a drive that's in that state, right? I think you all probably know that. That's pretty obvious. And so we make a determination that, yeah, the electronics are functioning correctly so that the rest of this stuff only operates as a substate of that state. So then we have some partition management. We have a grub manager that makes sure that our bootloader is installed and the system will be able to boot off of this drive. We scrub the drive for errors as well. That's a separate region. There's cache management on the device, making sure that we're disabling the right caches, those sorts of things. So I'm going to go ahead and pull the drive out of the system. And I'm going to cheat a little bit since this is not right in front of me. Actually, I think this is...
What? No minions?
No minions. I think everyone's gone home for the day, so there's probably no minions left. Okay, So this is going to go ahead and pull the drive out. And you can see some things happen here. We're actually doing a higher level transition. So what happens is the slot has transitioned from a state of drive present to drive missing. And all of those state machines underneath all clean up correctly and handle the proper shutdown procedure. In most cases, those just exit immediately. And then over here, I've got a separate region we're looking at. This is the region that handles the MD arrays. And we use the MD arrays just for our system partition. We just do a mirror, essentially, of our Linux host OS across all the drives. So you can see now we've gone into a state array incomplete over there. And when I reinsert the drive, we will see that the kernel detects it. We go back into drive present. In this case, we realize electronics are functioning. Oh, this is actually a previously known drive. We're now in this state. And this is an interesting state we added just because if a customer pulls a drive out and then they reinsert the same drive, we want to make sure that they really want to they actually want to do that before we just start putting data back on.
And all that data could be stale because you don't know how long it's been missing.
Exactly. So that's an intermediate state, and they will actually have to go into the UI and click, really re-add this drive. So we don't automatically do that, but I'm going to simulate the.
So what if the disk has been missing for hours and you reinsert it? Will there be some sort of a check if the data is still valid?
Yeah, so the data itself, that's going to be covered in my Scribe presentation. And that actually, because once I removed the drive, the Scribe system is already going to start remirroring that data that's missing there. So when we reinsert that drive, it doesn't really matter what's on that data part. Yeah, exactly. It's not going to even be referenced anymore. So what we see here is that we have a drive that's out, and I'm going to go ahead and force it back in. So what I've done is I've just triggered a transition in the state machine again to essentially move back into a drive known state. And you can see that the grub region is actually interacting with this state machine over here. It was waiting for the MD to recognize the device before installing the bootloader. That's a little interesting trick that you have to do before you install grub, because the machine might not boot if it's not in the MD prior to. We actually just discovered that last year, I think. So, but anyway, so you can see the drive is now back in. We've got an MD array. Our system partition is in recovery in progress, and that sort of thing. And these are all transitions that will have alerts tied to them and everything as well. So I don't know if I had a UI somewhere that I think might be closed.
So Phil, are you doing this from like a rules engine where you built all of these rules in it, or is it just hard programming within the code you've written?
We've programmed it in our state machine framework that's implemented in C++.
So it's like almost like a policy engine within the framework you have.
Exactly. So a lot of it's just based on knowledge we've gained over the 5 years of doing this, and it's like, wow, we have all these little cases that we need to make sure that are in the state machine. So
you can change that at any stage if you you have other things that come up. And is that going to be influenced by the way that Linux changes, the way that's rewritten? Is that going to be an issue, or is this because of the hardware technology, the way that say drives work with the manufacturers? Is what influences your?
And we've had that happen a few times where we have something if we get a new firmware release or something that operates differently, or we decide to start supporting a new RAID card.
Yeah.
You remember that data layer where you have the collectors at the bottom? Typically, honestly, it's very easy, and we have an engineer who will do that in probably less than a day. They'll rewrite the collector, and then everything will just work again. Right? And that's very, very nice. It gives us the ability to do some rapid development of that stuff. So let's see. So just kind of in summary with this management layer, we have that data layer with nothing but trusted information in it. All of our different components of the system rely on the same data layer, so the view of everything is very consistent. The state machines take the actions when conditions occur and attempt to correct those things, and an alert manager will notify via email and syslog set and cleared. We've actually seen a lot of cases where something will go wrong with their cluster, and they'll get an alert notification, and by the time support gets on the line, the system is basically correcting itself. The state machines move it back into a stable state, and the problem solved. So, and then again, the UI has direct integration and direct visibility into all of this kind of stuff happening. So that's our cluster orchestration layer.
So you are using Linux as a operating system.
Yes.
Now that dtrace, I think dtrace is also available on Linux. Do you think you can take advantage of that technology, or
sorry, can you say again now that what is available on Linux?
dtrace. It's originally developed on Solaris, and in the
dtrace.
Yeah. Does it make sense for you, or you already done a lot of work on Linux?
Yeah, I mean, at this point, I think for myself, and probably same with most of the engineers, we really enjoy working with this system at this point, especially from a troubleshooting perspective. I mean, it's gotten so easy and so quick to figure it out, and it's very easy to add and modify functionality in the system that I can't really say that we would consider it, but
I think they would make more use of dtrace if they were trying to troubleshoot the kernel.
Debug.
Yeah. As far as seeing what the state of devices are, there's not a whole lot of benefit to it. It's very powerful for what it's there for, but at this level, unless they're trying to track down core code issues.
They can get a lot of sensor from the kernel.
Yeah, which they can also get from the proc file system, and that comes default with Linux.
Yeah, a lot of what the collectors are doing is looking in, sysfs in the proc file system and just and looking at that interface there.